Ideal single-phase transformers. Hello everyone, my name is Rafael. I am an electrical engineer, and in this video I'd like to discuss with you ideal single-phase transformers, and to do so I chose this exercise. The purpose of this exercise is to stress the importance of transformers for electrical power systems. Let me read the exercise. Ideal single-phase transformers. A single-phase power system consists of a 480 volts, 60 hertz generator supplying a load Z load of 4 plus J3 ohms through a transmission line of impedance 0.18 plus J 0.24 ohms. Firstly, let's go to letter A and subsequently to letter B. Letter A, if the power system is as described by figure A, what will the voltage at the load be? What will the transmission line losses be? Okay, so this is the letter A. This is what we are going to do first. Firstly, we are going to analyze this system without the transformers, and subsequently with transformers, and see what changes. Okay, let's go to the solution. Of letter A. When there is no transformer in the power system, the current of the generator is equal to the current of the line, which is equal to the current of the load. Then Ig is equal to I line, which is equal to I load. Alright? It is clear. This equality is clear. And the voltage of the generator, the phasor, is equal to the voltage drop along the line plus the voltage on top of the load. These are complex quantities, okay? The current of the system can be calculated as, we are going to calculate the current here. We're going to call it simply I. The current of the system can be calculated as I is equal to the voltage of the generator divided by the impedances Z line plus the load. Okay? We simply use the values that the problem gave us. 480 phase 0 degrees volts divided by 0.18 plus J 0.24, which is the impedance of the line, plus the impedance of the load. You can use a calculator to conduct this addition and then this division, and you're gonna find 90.8 in the phase negative 37.8 degrees amperes. This is the current that passes in the system from generator to load. Therefore, the voltage at the load will be the voltage here at the load will be V load a phasor is equal to the current that we just calculated times the impedance of the load. We simply use the values. The current is this, 90.8 in the phase negative 37.8 degrees amperes, multiplying the impedance of the load. Four plus J3 ohms. Again, you are going to use your calculator. I am going to give you a clue. Convert this number from the Cartesian form to the polar form first, and then multiply with this. You multiply the absolute values, and then you sum the angles. Okay, this is how we conduct this algebraic multiplication. And then we find a value equal to 454 in the phase negative 0.9 degrees volts. Okay? This is the voltage at the load when there are no transformers participating in the system. Okay? You see that the voltage of the generator is 480 volts. and the voltage at the load 454. What if we want this voltage here there? The voltage at the load as close as possible to this. We are going to use some method, some piece of equipment to do this job. And the equipment that do this is a transformer. But before using transformers, let's calculate the power lost through transmission, the line losses. We are going to conclude that the losses without the transformers are much higher than the losses with transformers. So the line losses will be equal to the current squared times the resistance of the line. The current is 90.8 amperes squared times 0.18 ohms, and then we find that the power losses amount to approximately 1.5 kilowatts. 1.5 kilowatts. This is what's being lost along the transmission line. Now, what we want to assess is whether we can diminish these losses using a transformer. And the other benefit of the transformer that we wish to assess is whether the voltage at the load will be as close as possible to the voltage of the generator. So let's do it. Let's go to letter B. Okay, letter B, we are going to do this. We are going to erase here. And here. And we are going to connect transformers. This transformer here, T1, is 1 to 10. And this transformer here, T2, is 10 to 1. Okay? With these transformers there, we are going to go now to letter B. Let's read letter B. What does the exercise want from us? Suppose a 1 to 10 step-up transformer is placed at the generator end of the transmission line, and a 10 to 1 step-down transformer is placed at the load end of the transmission line, such as in figure B. So now, this is figure B. Questions. What will the load voltage be now? And what will the transmission line losses be now? We are going to calculate again the voltage at the load and the power lost along the line. Let's go. Let's go to exercise letter B. First of all, we are going to represent the system in an equivalent way, okay? We are going to refer, this is the idea behind this, we are going to refer this impedance to this side, and then we are going to sum the impedances, and then we are going to refer again to the generator side until we get something of the sort. Okay, first of all, let's eliminate T2 by referring this the impedance of the load to this side, and then we are going to get something of the sort. We are going to get this. Okay, we are going to get Z load prime here because we are referring Z load to the side of the line. Then let's do it. How do we do this? We are going to use an expression like this: Z load prime. Z load prime is equal to A squared times Z load. Okay? And what is A? A is equal to 10. The turns ratio of this transformer. Therefore, we get that it is equal to 100 times the impedance of the load, 4 plus J3. The Z load prime will be equal to 400 plus J 300 ohms. Okay? Are you guys understanding? Now, we need to do this. We need to combine this impedance to the impedance of the line. Okay? This is the next step. We are going to combine this impedance with this impedance here. And then we're gonna get a single impedance here. We're gonna get a single impedance here, which is gonna be ZAC. And what is ZAC? ZAC is the equivalent impedance, which is the impedance of the line plus Z load prime. Okay? Let us remember to calculate what we wish. Firstly, I referred Z load to the side of the line, and Z load became Z load prime. I use the turns ratio of this transformer to refer this load to this side. Then 4 plus J3 became 400 plus J300. Okay? Subsequently, we wish to combine this referred impedance with the impedance of the line, and this becomes Z equivalent. Let's calculate Z equivalent. Z equivalent is going to be 400 plus J300 plus 0.18 plus J 0.24, because they are in series. Had they been in parallel, we would need to use another expression, but as they are in series, we simply add them. And then we get the equivalent equal to, use your calculator. Use your calculator. You're going to sum this real part with this real part, and this imaginary part with this imaginary part. You are going to get a Cartesian representation, and then you convert it to the polar form, and you are going to find 500.3 in the phase 36.88 degrees ohms. So this is the equivalent impedance. To finish this process of referring impedances, we are going to do this, the following that I'm going to show you. The generator here, and then we are going to have Z equivalent prime. Okay, and the current of the generator is going to flow here. Whenever there is this symbol prime, it means we've referred the impedance from one side to the other. Now we need to refer this to the region of the generator, and to do so we are going to use the turns ratio of the transformer. Now the turns ratio is 1/10. Okay, so Z equivalent prime is equal to A squared times Z equivalent. Since A squared is 1 divided by 100, we need to merely divide this number by 100. And then we find that Z equivalent prime is equal to 5.003 in the phase 36.88 degrees ohms. All right. With this system at hand, we can calculate the current of the generator. The current of the generator is simply the division between the voltage of the generator and this equivalent impedance. The current of the generator is going to be 480 phase 0 degrees volts, okay, divided by this number here, okay. As it is a division, we divide this number 480 by this number here, 5.003. When dealing with the angles, we subtract 0 minus 36.88 degrees. And then we find that the current of the generator, I'm going to write it here, okay, 95.94 in the phase negative 36.88 degrees amperes. I'm going to erase here. This is the current that flows here, the current that flows at the generator side. And now, to calculate this current and this current, we simply use the turns ratio of the transformers. Okay, I line will be equal to 1 over 10, okay? That's why, the very reason we use transformers. The first purpose, pay attention, the first purpose for using a transformer is not to increase the voltage. Increasing the voltage is just a consequence. The purpose is to diminish, to decrease the line current. Why? Because high currents along lines are the causes of power losses. So we need to diminish power losses. And as we decrease the current, we increase consequently the voltage. So we needed to decrease the current to decrease power losses. The current along the line is going to be 1/10 of the current that flows in the generator circuit. 95.94 negative 36.88 degrees amperes. So I'm going to write it here. I line is equal to 9.594 in the phase negative 36.88 degrees amperes. Okay? So this is the current that's going to flow here. 1/10 of this current here. The other current that we need to calculate is the current of the load. the current of the load using this turns ratio is going to be equal to I load is going to be equal to 10 times the current of the line, which is then equal to 95.94 negative 36.88 degrees amperes. Observe that here there is a coincidence. The turns ratio of this transformer is equal to the turns ratio of this transformer. Now, let's calculate the voltage at the load. The voltage at the load will be equal to the current of the load times the impedance of the load. Using these values here, using this value here, and this value here, we find that the voltage at the load is 479.7 in the phase negative 0.01 degrees volts. Okay? Very, very, very much close to 480. Remember that in letter A, let's remember that in letter A, the voltage was, in letter A, V load was 454 approximately 0 degrees. 454. Now is 479.7. See that the voltage at the load is almost the same now as the voltage of the generator. This is a very big achievement for electric power systems because we can have the same voltage here and there. And now the power losses, the power lost through transmission is going to be I line squared times R line. And then we get this value here, this value here. We multiply by this, the resistance of the line, and we get P losses equal to 16.7 watts only. Only this. Without the transformer, the power lost was 1.5 kilowatts. Now the power lost is simply 16 watts. Okay? So this is the idea behind using transformers in power systems. The transformer enables the voltage at the load to be almost equal to the voltage at the generator. And the other benefit, and this is the purpose of employing transformers is that the power lost for transmission is going to be greatly diminished. Okay, my friends, this was the video that I wanted to make. I hope you guys enjoyed it and learned from it. I am a teacher. If you want to book a lesson with me, use my WhatsApp number, guys. Goodbye!